Welcome to session 8 and our third part on survival analysis. We're going to cover a lot of ground today. Your learning objectives are going to be learning to check model assumptions and fit of the Cox model through residuals analysis and the log minus log plot to fit and interpret multivariate Cox models. And some of this goes for all the kinds of multivariate models that you've learned, such as the test for trend, making predictions for specific covariate patterns, and predicting outcomes for adjusted coefficients. These are maybe less used, but they are potentially useful across all of the kinds of regression that you've learned. We're going to cover a bit about stratified analysis so that you will at least be able to explain what it means and understand it and eventually be able to perform it. You will learn to identify situations of competing risks. We're not going to get into the details of it or how to actually perform these analyses because it requires a whole additional session at least of its own, but we'll at least cover what it is and how to know when you're in this kind of situation. And I'm going to just introduce to you the application of propensity score analysis. Another one of these things that applies to everything that you're doing this semester and as an approach that you can possibly take. Our outline will start with a review and then track those learning objectives pretty closely. And I'm going to skip along because we have quite a bit to cover today. So starting with a brief review, recall that the Cox proportional hazards model, we introduced it for this situation where we have a potentially right-censored, meaning that we have information up until a certain point in time at which an event occurs or it is censored, and we don't know whether it occurred or not, or the event would have occurred at some time greater than where it was censored to. And with multiple predictors, which can be categorical or continuous. The proportional hazards model looks like this. We're modeling the logarithm of this hazard ratio, and you'll notice this hazard ratio is a function of our covariates, but it is not a function of time. Now the hazard ratio is a ratio of these two hazards, the hazard of which is a function of time conditional on the covariates divided by a baseline hazard function of time. So the hazard in general does depend on time, but this ratio of the hazard for any particular individual in your study, any particular participant to this baseline hazard is a constant over time, and that depends only on the covariates according to this linear predictor, as with all of our linear regressions. So this hazard ratio is a function of x. That's the hazard of a patient I relative to the baseline at all times. And this hazard function of time conditional on xi is the time-dependent hazard, something that we don't model directly in the Cox proportional hazards model. And then this h0 as a function of time was the baseline hazard. And just to recall, that's the negative of the slope of S0 of t, which is the baseline survival function. So that's the thing that we estimated with the Kaplan-Meier estimator, that was the cumulative survival function that always decreases over time. All right, some caveats and assumptions, and this first one is really just a caveat to watch out for. If you have a categorical covariate, then if you have a category with no event, such as especially if that group is smaller, its risk is low, then hazard ratios, if that is the reference group, then other hazard ratios will be infinite, and you won't have confidence intervals for them. So that's something to avoid. You can always make a different group the reference group, and then you'll have a zero hazard ratio instead for that small group. The issue is that because you have no events occurring in that group, then everyone you observe has zero risk. As far as you know, they will all live forever if survival is the outcome. So assumptions of the Cox proportional hazards model. I've mentioned that it is pretty robust. We don't make any assumptions about the form of the baseline hazard. So that the way that the baseline hazard, that everything is a ratio of, the way it changes over time doesn't matter. The only thing that we have to assume about it is that there's a constant hazard ratio over time, so that the way different participants in the study, the way their hazard ratio varies is just a constant ratio compared to that baseline hazard. We assume there's a linear association between the log hazard ratio and the predictors. That makes it a multiplicative model. That is, that additive changes in your linear predictor multiply the hazard ratio. An independence between survival times between individuals in the sample. This is the assumption of independence of observations, like we have had to make with all of the regression models we've done so far. We will, in our final couple of lectures, move past this with discussion of random effects models and hierarchical modeling. But for now, we're assuming independence between every observation. And then finally, the assumption of uninformative censoring. Put one way, a censored participant is the same as an uncensored participant if they have the same covariates. Another participant who is still at risk after that time. So the fact that one patient is censored doesn't tell you anything about when beyond that time they would be censored. All of that information is contained in their covariates. All right, so how can we check these assumptions of the Cox proportional hazards model? Well, we can perform residuals analysis, and I'm going to demonstrate that here using a simulated data set. One reason I'm doing this is because Pensim is my own package. This was actually my first R package that I wrote back in about 2011 or 2012, called Pensim, for simulating data for penalized regression methods. So that's one reason I wanted to do it. But another is that I can create some idealized data here to demonstrate these residuals analysis methods with. So I'm going to load the Pensim library here and create data with two variables, 500 samples, zero correlation between the variables, true coefficients of 0.5, and some other stuff that we don't need to know about, and some information on censoring, which is basically telling us that censoring is uniformly probable to occur at any time between 0 and 8.5. So this meets all of our assumptions. These are going to be independent variables. The censoring is uninformative. It's equally in that it is equally probable to occur for any participant between these time points. Anyways, what matters is what we've created here. For all that complexity, the data set's pretty simple. There's just two covariates. Variable 1 is categorical with values low and high. Variable 2 is a continuous variable. And then we have censored time to event. And I've simulated it so that all of our assumptions are met. We have proportional hazards, we have uninformative censoring, and we do have hazard ratios for each of these variables. They do have an effect on the hazard. So here's what our Kaplan-Meier plot of the data set looks like, just stratifying by our one categorical variable. And what we see is a nice, beautiful Kaplan-Meier plot. There's lots of censoring occurring here. You'll notice that there's less censoring up at the higher times, even though I had simulated this so that censoring is equally probable at all times, but we have more people at risk down at this end, so there is naturally more censoring, even though the probability of any individual having a censoring event, given that they're still in the study at this time, is the same. There are just fewer people. All right, so the first kind of residuals, the martingale residuals, these are sort of the most simple residuals to think about, although they end up having some problems. So all this is the censoring variable, that is 1 if it's an event, 0 if it's censored, minus the estimated cumulative hazard function, that is 1 minus the survival function. So for example, for a subject who is censored at 1 year, that is the censoring indicator is 0, whose predicted cumulative hazard was 30%, that means that they were expected to be alive at 1 year would be 0 minus 0.3. And for a subject who, let's say, had an event at 6 months and whose cumulative hazard at that point was 80%, their residual would be 1 minus 0.8. The problem with the martingale residuals is that they tend not to be symmetrically distributed, even when a model fits the data well. So here's an example with our data set. This is a plot of the martingale residuals. We have the two sets based on this categorical variable, for its reference value and its other value, and you see this this gradual decrease in the martingale residuals over time. So I don't know, for this reason, I'm not going to ask you to do the martingale residuals, and I don't even do them again in the lab for this session. The deviance residuals are scaled versions of the martingale residuals, so that they should be more symmetrically distributed, about 0. But as we see in this plot here, they're still not great. We still see this trend in the red line over time. All right, so here's a set of residuals that I actually do like, the Schoenfeld residuals. The technical definition of these is the contribution of a covariate at each event time to the partial derivative of the log likelihood. That means it allows for a time-dependent contribution of each covariate. A more intuitive interpretation is the observed minus the expected values of the covariates at each event time. So the expected value being the value that you'll get in your Cox proportional hazards fit, which is constant over time, and this observed being what it would be for observations at that particular time. But what's useful about them is that a random or just unsystematic pattern across event times gives evidence that the covariate effect is not changing with respect to time. Whereas if it is systematic, it expects that you may have a time-dependent covariate. All right, so here's what our Schoenfeld residuals look like for our simulated data. Remember, we have two variables. Variable 1 was the categorical variable, and we have one set of negatives, negative residuals, and one set of positive residuals. The average here is shown with a confidence interval, looks pretty much unsystematic over time. And with our continuous variable, we again see a more or less unsystematic variation over time. So this is a good set of Schoenfeld residuals showing that our assumption of time-independent covariates and proportional hazards looks pretty good. These also come with a test for proportional hazards that is essentially equivalent to fitting a linear regression model with time as the predictor and residuals as the outcome, and doing that for each one of the variables. It's a parametric analog to those lines that you saw on the previous page, or smoothed values of the residuals against time using a procedure called LOES, which is just fitting a curved line to a set of data points. And if the hazard ratio is constant, this correlation between time and the residuals should be 0. If there were positive values, then it would suggest that log hazard ratio for a particular coefficient is increasing with time. A negative value means that its effect is decreasing over time. So looking at variable 1 here, we have clearly no effect. Variable 2, there is maybe an effect, 0.026, but the global test for all variables is 0.079, which doesn't make significance. So this is probably just a false positive. And if I changed the set of random numbers and took a random sample, probably variable 2 would come out greater than 0.05 the next time. Here's a plot of the hazard function stratified by our categorical variable, and we see again here what looks pretty much like a proportional hazards, that the bar 1 equals high, this red dotted line is higher, it's shifted above. It's not perfect, but you have to remember there's sampling variation in here as well. And also a better plot for looking at this is this log minus log plot, and this is the log of the cumulative survival function and another logarithm of the negative of that taken. And we see more or less parallel lines here. There's some funniness down here at low time where there have been few events, but there's a lot of randomness involved here. For all of the places where we have more events and more censoring occurring, they're more or less parallel. So keep in mind this is an idealized example where the data are simulated so that we know that the proportional hazards assumption holds. All right, let's use some real data here. This is a data set that is included with the survival package. It's called the Primary Biliary Cirrhosis, or PBC data set. It's from a Mayo Clinical trial on primary biliary cirrhosis of the liver conducted between 1974 and 84 with 424 patients. It's a randomized placebo-controlled trial of this drug D-penicillamine, and there are 312 cases from the RCT plus another 112 cases that were not from the RCT. And the primary outcome here is a right-censored time to death variable. So just making a plot here of the treatment and placebo arms and looking at the survival probability over 12.5 years, and we see not a whole lot of difference. They track pretty close to each other. They cross over midway through, meet again later. So this does not look like an especially effective treatment. All right, we're going to continue using this data set, but I'm going to start talking about some new concepts here, starting with tests for trend. So tests for trend are relevant in a multivariate model that includes an ordinal variable, such as cancer stage 1, 2, 3, 4, where stage 1 would involve the lowest risk or hazard, and stage 4 the highest hazard, or age categories, where increasing age confers higher risk. And we use tests for trend to address questions like, is there a linear or quadratic or cubic relationship between coefficients and their order? And then we test these polynomial terms, again, either using likelihood ratio tests to compare like a full complex model to a base model, or Wald test for individual coefficients. So looking here at this PBC data set, again, these are stage data and the coefficient for them, and we see what does look like a trend. So stage 1, 2, 3, and 4, and every one of them is higher, and it does look approximately linear. So it looked like we had a trend, and a test for trend is a way of testing that hypothesis of there being a trend. This is actually very easy to do in R. All you have to do is define that stage variable, the categorical variable, as an ordered factor, and then tests for trend are done automatically. And you've already done some things with this factor function. All you have to do is add this value ordered equals true, and I'm creating a new variable here called stage ordered, and then using that in a regression, and that is all I'm doing. And then what I see in the output here, so I'm using only that stage ordered variable as my predictor. I see these three terms. The L stands for linear, the Q stands for quadratic, and the C stands for cubic. And I see a positive coefficient for linear with a significant p-value from the Wald test, and then these other two do not have significant p-values. The overall likelihood ratio test and the logarithmic tests are very significant, so we've confirmed what we saw with our eyes, that there does appear to be a significant trend and not something that is likely to have happened by chance. All right, our next topic is predictions for specific covariate patterns. So this is when we're talking about predicting the risk for a particular group of patients. So the Cox model is a relative risk model, meaning that it only predicts the relative risk between pairs of patients. It does not actually predict the absolute risk or the absolute survival time or expected survival time for a patient. So the key to doing this is to calculate an overall survival function, which we've learned how to do with the Kaplan-Meier estimate. And you've also, if you did the data science unit relating to this section, you've also done using SERVREG and a parametric model for estimating S of t. But either way, you calculate this overall survival function and then just multiply it by the relative hazard for the specific covariate pattern by that relative ratio. So in this example plot, I'm going to plot the overall baseline survival for all stages, and then for stages 1 to 4 separately. So here, this black line, this is the Kaplan-Meier estimator. So this is calculated directly from the data, that survival function S of t. And then with each of these other lines, I have just multiplied this line by my coefficient for stage 1, 2, 3, and 4. So you see that for stage 1, which had a much lower hazard, you have a higher survival. And we have a line right up here For stage 3, it had a hazard ratio very close to 1, and it sticks fairly close to the black line. And what you'll notice is that every one of these little shapes in the curve is the same in these plots because it's just this line multiplied by something. So this is not like those stratified Kaplan-Meier plots where we recalculated the survival function for each strata. This is a predicted survival for each covariate pattern. In multivariate Cox proportional hazards, the model formula, coding, and the objectives are the same as what you've done for LM and GLM. You use this for controlling for confounding, testing for mediation, testing for interaction. So here's an example from our PBC data set. Our censored time to event as modeled by age, sex, edema, stage, and the arm of the trial. This pbc.os, by the way, I didn't show the code here. I did it with echo equals false, but this is just a version of the data set where I removed incomplete cases for the survival data and the treatment data. So I'm fitting a multivariate Cox proportional hazards model, and then looking here at the coefficients. This looks similar to many of the regression output tables that we've seen. We have a column of coefficients. We have a column of the exponents of those coefficients just for convenience because the coefficients are log hazard ratios. This column is the hazard ratios themselves, and then standard errors on the coefficients, values of z for the Wald test, and p-values from the Wald test, showing us, for example, that yes, age is a continuous variable here, does have a positive coefficient. This is saying something like every year of age, to the extent that it is linear, results in about a 3% multiplicative increase in hazard, and that is significant. We would probably, if we were taking this analysis more seriously, want to add additional coefficients, polynomial terms for age, or categorize it. And then edema also is highly significant. This has a hazard ratio of 8, so the patients with edema have a much higher risk of early death, and stage as well, as we've seen in that previous plot. This lower part here is just the same information with confidence intervals given on the hazard ratios. So these are all hazard ratios, not coefficients down here. And overall tests just telling us down here that yes, the addition of all of these variables certainly does help us to predict survival relative to a null model where everyone has the same probability of survival. The one thing that is not significant in all of this is treatment. All right, this is getting a little bit specific here, but it's kind of interesting, and I just wanted to briefly show it to you so that it is something that you can do if you want to. I showed you how you could predict survival based on coefficients. We did it for stage in a simple model with stage as the only predictor. Well, you can also do it for adjusted coefficients. So we did it before for crude or unadjusted coefficients, but we can also do it with adjusted coefficients. So here's that model that we fit before with just stage as the predictor. These are the unadjusted coefficients. And then I'm going to do it again in an adjusted model where I again have stage, but I have all of these other variables in the model as well. So I get a new set of coefficients for stage, but these are part of a multivariate model where we have corrected for all of these other things. Whether or not that is advisable in this case, I don't know. Clearly, the treatment arm in a randomized trial is not a confounder, but it's also not doesn't seem to have any effect on the outcome. So it's probably useless at worst. So I'm showing here the hazard function for a baseline group, which is stage 1, and then I am adjusting that by this formula that I've shown here, and there's code for this underneath the lecture notes should you ever want it, but I'm just exponentiating this survival function according to my beta coefficients for stage equals 4. Doing it first with the adjusted coefficients, and you see still a pretty large decrease in survival, and then for the unadjusted coefficients, and you see an even larger decrease in survival. So you don't need to do this semester, but should you want to do this for an analysis, the code are available on the GitHub page for this lecture. All right, stratification, and I apologize we're covering so many things today, but stratification is relevant to all kinds of regression, not just survival analysis. So it is something important for you to know about. And all it is when an analysis is split into different groups or strata and performed within those groups and then pooled together. So some requirements: you need to have an adequate number of events in each stratum, at least 5 to 7. I don't know, that's very rough. In survival analysis, you probably need more than that, or you need at least that many events, not just not just participants, but actual events. This can be used to adjust for variables with a strong impact on survival, in particular variables where the baseline hazard is different. And so it can help solve proportional hazards violations because these strata can have different baseline hazards. The whole thing about how this is done in survival analysis is that the coefficients and hazard ratios are calculated within stratum and then combined. And no matter what kind of regression you're performing, the essence of it is that your analysis is performed independently in each stratum and then combined across all of the strata. So here's an example. It's very simple to do. All you have to do is add this strata function to your model formula. So I'm going to perform here a Cox proportional hazards regression of the PBC data set with the treatment arm as a predictor and stratified this time by stage. And when I do a summary, it appears basically the same as a univariate or crude analysis with just this treatment analyzed. So this is not the same as controlling for strata. It is instead a way of allowing for different baseline hazards in the strata. But ultimately, we're assuming the same hazard ratio in every stratum because we end up averaging them together and getting a single hazard ratio for treatment across all of the strata. All right, our final section, I just want to introduce two competing risks data. I'm going to use an example that is discussed in your textbook, section 6.5 from this MROS study that followed men over 65 to examine predictors of bone fracture and low bone mass density, which is a subclinical stage of bone loss. And at the end of the study, participants had either developed a fracture, and this was the outcome or the event of interest, or they remained alive without a fracture, which is one form of censoring or incomplete follow-up, or they died prior to a fracture, which is another form of incomplete follow-up. So we have these two kinds of incomplete follow-up here, and why not treat them the same? So why not treat those who died prior to fracture the same as those who were alive without fracture, just as censored events? Well, recall that independent censoring assumption that censored people are similar to those who remain at risk in terms of developing the event of interest. That may be true for the patients who were alive without fracture at the end of the study, but it's certainly not true for those who had died without fracture. They're not similar to those remaining at risk. So this violates our assumption that censoring is independent of the event of interest, or we assume that censoring is independent of the event of interest, and that is pretty suspect for patients who died. So we have some patients who are censored who are still alive, and some who are censored who have died. So just recall these reasons for right-censored data. One is just the cutoff date of the analysis. And this is the best possible scenario because that censoring is probably independent of the patients. It's just the study ended, we don't have time to follow up any further. A second is loss to follow-up. That is that someone moved or returned to their home country, and this is a bit more problematic if the sicker individuals tend to discontinue participation in the study due to lack of energy or just not feeling well enough to continue. And the key thing is that in these cases, it is something relating to their outcome that predicts censoring. It's not their covariates. It's not that they are males, even if males being male both contributes to being sicker and to dropping out of the study. That wouldn't be the issue. It's if the sickness itself is predictive of dropout. Or another example is if healthier individuals discontinue participation because they don't feel the need to continue, or they decide to go on and move to another country. And then the third situation is competing risks. That is where there is another set of risks besides the ones that we are modeling. And these are often informative risks. But in a competing risk analysis, then independence between the competing risks is not required. So I'm just going to give a very brief summary of what is involved in competing risk methods. So this one-to-one mapping that we've had between hazard and cumulative incident function before we had this capital H that was just like an accumulation of the hazard, that's lost in competing risks because we have actually more than one risk. In this case, we have a risk of bone fracture and a risk of death. And in situations like this, that standard Kaplan-Meier estimate is actually biased. And there's another estimator called the Allen-Johansson estimator that is a better choice, and you can estimate multiple hazard functions simultaneously. And this test called Gary's test is analogous to the log rank test in the absence of competing risks. It is possible to fit a cause-specific standard Cox proportional hazards model that would just treat all of the competing risks as censoring event, and that might be useful for for prognostic testing, that is just predicting survival probability, but not for estimating a hazard ratio in the population. Okay, so what is propensity score analysis? First of all, it's an alternative to the multivariate regression that you have learned for controlling for hypothesized confounders in observational studies. So the approach that you have learned is to take your outcome variable and model it as an effect of your exposure as well as your hypothesized confounders, and then look at your coefficient of the exposure after correcting for these hypothesized confounders. So that is a perfectly valid way of attempting causal inference. But propensity score analysis is a stratification alternative that is more practical than stratifying and performing your analysis separately on multiple hypothesized confounders. And it does this by summarizing potentially many covariates into a single score, the propensity score. And that makes it convenient for controlling for many hypothesized confounders. So how does it work? Well, the first step is to fit your propensity score model. So the outcome is not involved in this part, but it is where you predict the propensity for exposure based on confounders. So if your exposure is binary, such as exposed, not exposed, this is going to be a logistic regression model. And so all it is a prediction model of your exposure as predicted by your confounders. And then the second step is to use the propensity predictions from step 1 to match or stratify participants with similar propensity. A very simple example would be to use the quintiles of propensity. So you would organize your participants into 5 categories from lowest propensity score to highest propensity score of exposure. In your third step, you would check the adequacy of this matching or stratification. So you're somehow using the propensity scores to group together similar participants, those that have similar probability of being exposed. And this can be done by just comparing the attributes of the matched participants and by comparing the propensity scores of the exposed and unexposed groups within these strata. And what we expect through this matching is that participants within a stratum are approximately equally likely to have been exposed or not, based on predictions by these confounders. And then step 4 is to test your hypothesis about the relationship between outcome and exposure in a simple univariate model like this, but among the matched participants. And you can do this in a simple model now because you're directly comparing people who were approximately equally probable to have been exposed as predicted by our hypothesized confounders. So that's all I'm going to introduce about propensity score. Here are a few references. These are nice papers with reasonably straightforward introductions to the topic. And I'll just say you don't need any special packages to do a basic propensity score matching. It could just involve logistic regression, and then stratifying your participants by quintiles of the predictions. You could use the predict function on your fitted model and then use cut to split it into quintiles. But it might be easier using this match it package that will provide multiple matching approaches, diagnostics, and good documentation. They have several so-called package vignettes that are these sort of long format documentations, a little user manual, if you will, or a booklet. That's all for today. Thank you.